We may have completely misunderstood the universe. Nobel Laureate Adam Rees reflects on a new cosmological crisis. In the vastness of space, every beam of light carries a story. But what if those stories, now told with unprecedented clarity by the James Webb Space Telescope, JWST, are revealing a truth that upends everything we thought we knew about the universe? Professor Adam Rees, Nobel Prize-winning astrophysicist and one of the world's leading experts on cosmic expansion, has issued a sobering and profound warning. Our understanding of the universe was completely wrong. This isn't scientific hyperbole. It's the honest, unsettling conclusion from a body of evidence that grows with each new observation from JWST. What was once a coherent picture of cosmic history, one that began with a Big Bang 13.8 billion years ago and unfolded in an orderly progression of star and galaxy formation, is now being challenged by anomalies that simply don't fit within the established framework. The cosmic crisis, when observations refuse to obey theory. One of the most provocative revelations came with JWST's detailed imaging of galaxy GN Z11, also known as GZ9P3 in some earlier cataloging, a seemingly impossible object located over 13 billion light-years away. According to current cosmological models, such galaxies shouldn't even exist at that epoch, let alone exhibit the complexity and mass that GZ9P3 clearly displays. GZ9P3 existed just 510 million years after the Big Bang, yet it's already a mature galaxy, complete with a double nucleus, complex internal structure, and a stellar population that includes both young stars only a few million years old and older stars over 100 million years old. Furthermore, its metallicity, a measure of the abundance of elements heavier than helium, suggests it has already undergone multiple generations of star formation, contradicting the simplistic view of early galaxies being primitive clusters of first-generation stars. Population 3. Even more astonishing is the galaxy's mass. GZ9P3 is 10 times more massive than most other early galaxies detected at similar redshifts. It shows clear signs of having undergone a major galactic merger, a process we previously believed would take billions of years to occur. And yet, here it is, just 500 million years after the universe began, already behaving like a galaxy from a much later era. Webb's window into the early universe. JWST was launched with the aim of peering further back in time than any telescope before it, into the so-called cosmic dark ages, when the first stars and galaxies were forming. But what it has found is not a misty realm of diffuse protostars and primordial gas clouds. Instead, it sees well-formed galaxies, structured spirals, stellar bars, and even chemical signatures of advanced stellar populations. These observations are not isolated. Several early galaxies detected by JWST display the same surprising traits: massive size, complex structure, and evolved chemistry. What once appeared to be faint smudges in Hubble's limited view are now revealed as sophisticated cosmic cities, bustling with billions of stars and teeming with elements forged in multiple rounds of stellar birth and death. This isn't just an observational quirk or a random statistical outlier. It is a pattern: the Hubble tension and the expansion crisis. For years, Adam Rees has been investigating a different cosmic conundrum known as the Hubble tension, a discrepancy between measurements of the universe's expansion rate derived from nearby observations, using Cepheid variables and supernovae, and those based on the cosmic microwave background radiation, CMBR, the afterglow of the Big Bang. CMBR-based calculations yield an expansion rate, Hubble constant, of about 67 kilometers per second per MPC, while local measurements suggest a faster expansion rate of 73 kilometers per second per MPC. That difference might seem small, but its implications are enormous. It suggests either a systemic measurement error, or worse, a fundamental flaw in our model of the cosmos. JWST was hoped to serve as a cosmic referee, settling the score by measuring distant galaxies with higher precision. But instead of resolving the tension, JWST confirmed the discrepancy, independently verifying the faster expansion rate seen in local measurements. The result? A deepening mystery. Rees said in an interview with the Astronomical Journal, "Somewhere between these two observations there must be a fundamental flaw in our understanding of the universe." a crisis, or a new beginning. For some scientists, these accumulating contradictions represent a crisis. But for Adam Rees, they mark the dawn of a new era in cosmology. As he puts it, if our previous measurements of the universe are not correct, the determination of its age, the idea of expansion, and even the idea of a Big Bang as we understand it could be wrong, or at least not quite right. He's not alone. Increasingly, theorists and observers alike are beginning to consider radical revisions to our cosmic narrative. Some possible implications include: the universe may be older than we thought. Dark energy, the force behind accelerated expansion, may not be constant or uniformly distributed. Dark matter might behave in more complex ways than current models suggest. Our cosmological assumptions, especially regarding early galaxy formation, may be fundamentally flawed. A new force or unknown field could be influencing the evolution of the cosmos, challenging the sacred tenets. The old cosmological model, grounded in general relativity and inflation theory, held that galaxies formed gradually, growing from small clouds of gas and stars into massive structures over billions of years. But Webb's observations point to a universe where massive, evolved galaxies appeared extremely quickly, too quickly to fit the standard model. Even the notion of population 3 stars, the theorized first generation of stars made solely from hydrogen and helium, is being called into question. Where are these massive, short-lived stellar giants? If they existed in abundance, JWST should have spotted them. Instead, what we see are metal-rich stars, evidence that several generations have already lived and died before the light from these galaxies reached us. What comes next? As of now, scientists remain cautious. Rees and many of his colleagues stress that more data is needed. Webb is still in the early phases of its mission, and while its discoveries have shaken the foundation of cosmology, they also provide a roadmap for building new, better theories. Yet the implications are inescapable. If galaxies like GZ9P3 really are as evolved and massive as they seem at such early epochs, then either our understanding of time, space, or the physics of the early universe is deeply flawed. The universe reimagined. In the end, perhaps the most revolutionary truth is not that we've been wrong, but that we're finally beginning to see how much more there is to learn. As Rees notes, the universe is not just bigger, but stranger than we ever imagined. These discoveries are not failures, they are opportunities. They tell us we've reached the limit of our old theories. And now, we must go beyond. Whether this leads to a revised Big Bang model, a new form of cosmological inflation, or even a multiverse scenario remains to be seen. What's certain is this: we are witnessing the rebirth of cosmology, a time when new instruments, new data, and new ideas converge to challenge everything we thought we knew about our place in the cosmos.